Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
So cute. Hi, everyone. I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a friend to the universe. It braided my hair last week.
I need someone to help me braid my hair, so I'm going to ask them. I'm Corinne Caputo. I'm a writer and a fun person, and I've tried to braid my hair today, but when you have layers, it just doesn't quite work.
It seems tricky. Let's see. Yeah, what's around us? Where are we, Corinne?
We are in a cocktail bar, and it's one of those cocktail bars. It's like a little underground. Like you feel like you're underground, but you're not. Just like the lighting and there's some red neon lights, but like the drinks are really good. It's not overpriced and it's not too crowded. So it's kind of this sweet spot of, you know what, this drink could be bad and I wouldn't care because the vibe is good, but we're lucky the drinks are still good.
That's the perfect spot. I'm so glad you found this. Thanks for bringing me here.
Yeah, it's a secret. I can't say the name.
It's extra secret. This is like a speakeasy. We had to say a password on the way in. So, listeners, you have to be cool. You have to find it yourself. Is there any particular reason you wanted to come here other than it's just cool?
I needed a drink, and I just wanted to taste something complicated and good more than the seltzer that I've been at home with. They do a really good Negroni here, and Negronis are just equal parts gin, vermouth, and Campari, I think. So it's hard to do like a good one because that's just what it is everywhere, or should be. But this place does a coconut washed one, or like a fat washed one. So I tried to replicate it at home, and it came out really bad. So we had to go get it for real.
Amazing. So that's obviously what you ordered. I got a very fruity mocktail with a passion fruit base.
I love passion fruit.
I know, me too. And it's summer. It feels so appropriate. So let's cheers.
Cheers.
To today's topic, which is a really powerful and long-awaited telescope, I will say. We're talking about JWST today. Its government name is the James Webb Space Telescope. I am in a camp of astronomers who I don't really like to use its government name, so I call it JWST. A lot of people will call it the Just Wonderful Space Telescope. I've also heard Jellescope, Wellescope Space Telescope, or the Jelly Welly Space Telly.
That's fun.
Yeah, but that's what we're talking about today. Corinne, have you heard of this telescope?
I have heard of it.
Good. I would have been shocked if you'd said no.
Yeah, imagine. No, I have heard of it. I honestly don't know when I first heard of it, but it's a newer telescope, if I'm not mistaken, and it's where a lot of our coolest pics have come from.
Yes, exactly. It is newer. It launched in 2021, although we've been talking about it since the 80s. That's how far back the planning for this telescope goes. So we're going to get into the history. But Corinne, what would you like to know about JWST by the time this episode is over?
First thing that came to mind is size. How big is it compared to me? That's kind of, how do I immediately relate this to me? But that's human instinct. And I'm curious about how big it is. I'm curious about how much it cost. Because things in space and things in general cost way more than I think they should.
And this telescope does have kind of a reputation for being really expensive.
Yeah, that's kind of the rumor that I know of. That's the rumor on the street. And yeah, I'm just kind of... Is it JWST when you look up like pictures from your birthday? Are they JWST pictures?
A lot of them probably would be JWST pictures, but I think you are thinking of APOD, Astronomy Picture of the Day.
Yes, that is what I'm thinking. Okay.
Yes.
Well,
and recently a lot of APOD pictures are JWST pictures because they have this telescope has given us such gorgeous images.
Love it.
All right, then I definitely have the answers to those questions for you about the size for sure. But first, let's get into how this telescope came to be. I said that conversations about it go all the way back to the 80s, which, in case you aren't familiar with, the timeline of astronomy NASA telescopes, is before Hubble was launched. The Hubble Space Telescope launched in 1990. So even before they launched Hubble, they were already thinking about the telescope that would succeed it. That's the one that comes after, right?
Yes, like Succession.
Okay, there you go.
The show. So I'm going to remember.
I hope that out there's someone who gets an SAT question right because they watched Succession. So conversation started in the 80s, but I think we can really trace the origin of it back to September 13th, 1989. This is the first day of a workshop held at the Space Telescope Science Institute in Baltimore, Maryland. The Space Telescope Science Institute, also sometimes called STSCI, although the cool kids in astronomy just call it Space Telescope. So that's what I'm going to call it. Space Telescope was established in 1981 to operate the Hubble Space Telescope. So they hosted this workshop from September 13th to 15th, and it was called the Next Generation Space Telescope Workshop, where they were proposing Hubble's successor, and they had a couple different ideas of what it could be. It could either be a 10-meter near-infrared telescope put in a high Earth orbit, or it could be a 16-meter telescope put on the moon, which had never been done before, put on the moon, and both of these would be to study galaxies at really high redshift, so galaxies that were formed early on in the universe, so we can see them how they were, up to 10, 11 billion years ago. It's a long time. Actually, we've seen galaxies that were, 13 billion years old, so really far back.
Putting one on the moon, I don't think we have done that since then.
No, you're right. The way I said that did kind of imply that we've done it since, but we haven't.
Well, I was just curious if, we didn't do it this time, but maybe we did it again. But I was like, I don't think there's anything really on the moon right now besides the garbage we left there.
Right. There are a couple of instruments that can measure seismic activity. We left a mirror there so that we could bounce light off of it and really accurately measure how far away the moon is. And that's one of the ways we know the moon is moving away by about 1.5 inches every year. So we did leave some useful science things there. But we haven't put a full telescope on the moon yet. I say yet because I just attended a conference last week in Oxford, and one of the talks at the conference was about putting a telescope on the moon.
Whoa, fun.
Very fun. I really enjoyed that conference. I hope that I can put together a full episode in the future, but I am waiting for permission from the conference organizers. So those were the two proposed ideas. That was 1989. They wrote this big paper coming out of the conference being there were 130 astronomers there. And they wrote this paper saying, this is what we think we should pay attention to or focus on in the next generation of space telescopes. Flashing forward 7 years, we're in 1996. Both of us are now alive. Corinne?
Yes. I think I'm in kindergarten. I don't know.
Great. I'm
learning.
Fresh babe.
I'm learning something somewhere.
My neurons are connecting rapidly. In 1996, a scientist named Alan Dressler is made the head of a committee of 17 other astronomers to put together a report for NASA on the future of UVOIR astronomy. If you are ever digging into astronomy history papers and you see UVOIR, all in caps, that's an acronym for ultraviolet, optical, and infrared astronomy. So most of the wavelengths regions of the electromagnetic spectrum, but not X-ray, not gamma ray, and not radio waves.
Okay.
Or microwaves, actually. So it's just the middle part of the electromagnetic spectrum. And that's where we do a lot of our observations, especially back before we had better capability and better technology. Mm-hmm. Okay, so Alan Dressler and his committee, they're putting together this report for NASA where they formally recommended for the first time that, and I quote, NASA should develop a space observatory of aperture 4 meters or larger, optimized for imaging and spectroscopy over the wavelength range from 1 to 5 micrometers, end quote.
A famous, iconic quote from NASA.
I just wanted to get the details right. I found the actual report. This long report is available for our patrons who get research notes for every episode. So if you want to read through it, then you can. And you can find other iconic quotes. So in that iconic quote, they say 4 meters. That's their goal for the next generation space telescope. But that's not very large. And so some NASA people saw that and they're like, is that really all you want? Like, why not push for more? And so through conversations, through in-person conversations at the 1997 Winter AAS meeting, that proposal got expanded from 4 meters to 8 meters or larger. And then it was funded by NASA, just like through conversation. Like, astronomy really is done on such a personal level.
Yeah.
Which I love.
I like that.
And also kind of hate. Because it leaves a lot of room for like the old boys club.
Yes.
Or
you got to be in the know. And also, not everyone is conversationalist. Like,
exactly.
You don't need to have the most suave social skills. You shouldn't have to be a salesman, too.
Mm-hmm, mm-hmm. But that's why they put the people in charge of these observatories or these big missions. The principal investigators are usually the more charming ones because they can get the deals made.
Yeah, yeah.
Mm-hmm. So NASA gave them a little bit of funding to further develop this idea, and over the next few years, it gained some steam. Several talks at conferences were given about the Next Generation Space Telescope, and it was recommended as a priority for the community in the 2000 Decadal Survey. So by 2002, NASA had said, like, yep, we're going to do this. They selected teams to actually build out the Next Generation Space Telescope, as it was called, up until September of 2002. So now we're talking over a decade of it being called the Next Generation Space Telescope, and they decide to change the name in September of 2002 to the James Webb Space Telescope. Construction begins in 2004. They plan to launch the telescope in 2007 in French Guiana. And then a lot of delays happen.
I was going to say, I'm pretty sure this did not launch in 2007 or even in the ohhs.
No, it most certainly did not. So originally planned for launch in 2007, it then got pushed to 2014 because they realized they needed to build a lot of new equipment. We hadn't really done much with segmented mirrors. I don't think we had ever put a segmented mirror up in space before. So we needed to come up with some new inventions before we could launch this telescope. In 2011, all 18 of the mirror segments had been completed, and they started constructing the whole telescope, the mirrors plus the backing plus all the instruments. They started constructing them at NASA Goddard in Maryland. And after 2011, then we really enter into the delay era. I have a list here of a select list of some of the reasons launch for JWST was delayed. Several categories of testing just dragged on longer than they should because they wanted to make sure this would be a robust telescope. A contract that they had with their launcher in 2015, they signed a new contract with their launcher saying that they would launch in October of 2018, again, realizing that they needed a lot more time to develop all of the tools they would need for this telescope. So by 2015, they're like, okay, we have 3 more years. We are going to launch in 2018. No. Then there were issues with the propulsion system. Then there were issues with the sun shield that they used to protect the telescope from solar energy. Then there was COVID. And then there were issues at the launch site where it maybe wasn't stable enough for a launch for some reason. Then there was an accident where a clamp released a part of the telescope and it caused some bad vibrations that they needed to fix. Then there were some electrical issues that affected the communication system, so they couldn't communicate with the telescope, and obviously they're not going to launch it if they can't talk to it. And then there was bad weather.
Oh, no.
So many things went wrong, but I'm glad that they waded through all of those and that they did all of the requisite testing because this was something that we couldn't get wrong. We only had one shot, so we had to make sure it was going to work. But people genuinely were terrified that this telescope wouldn't launch and deploy correctly. I know for a fact that my colleagues in astronomy had nightmares about JWST not working. My advisor in grad school dressed as JWST for Halloween in 2019 because it was the scariest thing he could imagine.
So funny. Oh my God.
So this is how wrapped up in JWST news the astronomy community was in like 2019 to 2021. It finally launched on Christmas Day on December 25th of 2021.
What a present.
I know. I remember that day. I woke up thinking, like everyone did, that it probably wasn't going to happen because it had been delayed so many times up until then. And when it did, I was shocked and so ecstatic. I was in a cabin up in Maine when it launched.
Aww.
You asked about the money, and
yeah.
it's surprising. How much do you think in total JWST cost?
Oh my God. From like since the 80s?
Yeah, in terms of all of the development for it.
Oh my God.
And launching.
This feels like $1 billion event.
$1 billion.
Yeah. Is that right?
No.
Okay, $10.
We wish.
$10.
$10. No,
Somewhere
Corinne,
between
that was your $1 billion estimate was an underestimate.
I thought for sure I was overestimating.
Absolutely not.
Because it's such a big number.
I know.
Oh, no.
So the initial budget when Alan Dressler proposed the Next Generation Space Telescope back in the 90s was $500 million.
Okay.
Which even then was a low amount. It was 1/3 of Hubble's cost to build and launch. So I imagine they were hoping that because more time had passed, they had better technology and things would be cheaper.
Yeah, I don't know why people think that. They're like, well, we did it for this price last year, so we could do it for less this year. And like, no, everything's going up.
Way too overly optimistic. Also, in the meantime, there were like government and administration turnovers, and NASA was getting less funding, and it was a tumultuous time. In 2002, when the corporate contractor Northrop Grumman joined with the project, the proposed budget was increased to between $1 and $3.5 billion.
Wow.
So they knew then. It was like, this is going to cost more than $1 billion. Because Hubble cost $1.5 billion.
Yeah.
But that also was an underestimate. All of the testing, all of the delays, all of the labor hours that went into like doing the research and development, it added up. And so by 2021, when the telescope launched, NASA and the collaborators, the European Space Agency, had spent $8.8 billion.
8.8?
Yes, on just developing and building the telescope and launching it, and then an extra almost $1 billion, an extra $900 million is allocated for maintaining and like operating it for a 5-year mission. So in total, and adjusted for like inflation, which is a weird calculation, but over $10 billion will be spent on JWST over 24 years.
Wow. That's a lot of money.
It's so much money. And it got a lot of flack for it. There were people posting opinion pieces about, imagine all of the other telescopes that could have been deployed if we hadn't wasted all this money on JWST. But ever since we got even those first images back from JWST, I have heard all of those people be so quiet. I have not heard a single peep from them because everyone understands that this telescope, even in its first year, gave us enough information to be worth it. Yeah. And also, over those decades, JWST never cost more than 3% of NASA's annual budget.
Oh.
Yeah. So it was a small part.
Okay.
I'm ready to tell you about the size. Corinne, you would be quite small next to it.
Love that. Reaching my borrower's dream.
How big across do you think it is?
Is it larger than the ISS?
It's smaller than the ISS.
Okay, so
in total, yes.
So it's smaller than a football field.
To be fair, I'm also just the mirror, just like the mirror part of it. How big across do you think that is?
You know, I'm realizing I have no idea. Maybe like 30 yards. Which is a number I've picked out of the air, which is 300 feet. I don't know what that is in If I were to...
30 yards is 90 feet, Corinne.
Oh my God, you're right. I'm multiplying it by 10. Okay, so somewhere between 30 yards and 300 feet.
It's smaller than that. It would have cost probably like $100 billion if we were trying to make it.
Well, they should think about that for next time.
Next time. You know, they probably already had a workshop to plan it. Like 10 years ago.
Yep.
It's 6.5 meters across. So maybe about 20 feet across.
All right.
Yeah. That's the diameter of the mirror, but the mirror isn't a perfect circle. It's more of a hexagon. It has a hole in the center, and it's made of all of these different parts. When I say segmented mirror, picture like a fly's eye, how it has all of those parts that work together.
Yeah, okay. That's fun.
Yeah, so there are 18 parts in total, and when you add up the collecting area, which is a really important value for a telescope because that tells you how much light the telescope can collect at one time, it's about 25 square meters or 270 square feet.
Okay.
So, like, there probably is an apartment in New York that
I was going to say,
small.
Compared to an apartment.
Like, there probably is a studio somewhere that's the same size as JWST.
Sure. It can fit perfectly in.
Or if you, like, break it up, you could map it out like a puzzle. How much do you think it weighs in total?
Oh, my gosh. I don't know, like 3 cars. Is that way too much?
I don't know what a car weighs.
One car weighs exactly a third of the JWST.
Then you're right.
No, I actually don't know. A car is like car weight.
I think it's like a couple tons, like 2 tons.
Yeah, like
4,000 pounds.
The average car in the U.S., which I feel like is probably skewed towards heavier because of the size of our cars here, is about 4,000 pounds.
Then Corinne, yeah,
3 cars.
Yes, it's Why are you so good at this most of the time?
I mean, I got the billion one wrong, but that one I got.
That was amazing. Yeah, it weighs 13,700 pounds.
Okay.
Good for you.
Not bad.
You. Or 3 large American cars.
3 American cars.
three American trucks.
Yep.
3 Ford trucks.
Sounds right. Hey, it's me, Corinne. I want to thank our patrons as always. So a huge thank you to our Sun-like stars, Scott Reynolds, Ian O'Leary, Augustin, and Tom T. And of course, you, listener, can support us, hear your name on the show, make it to our patron star chart, all by supporting us on Patreon for just about $1 per episode. You can find the star chart, Patreon info, and more at our website, palebluepod.com, or by going right to patreon.com/palebluepod. And if you can't support us financially, we love you so much anyway. That's totally fine. Support us by reviewing the show on whatever app you use and sharing it with your friends. And before you go, if you are loving Pale Blue Pod, which I hope you are, and especially if you're loving Dr. Moiya McTier, you have to give her other podcast, Exolore, a listen. If you didn't know, Moiya is also a folklorist, so if you've ever wondered about what life would be like on different planets, or how writers create your favorite fictional worlds, Moiya has the facts for you. On Exolore, Dr. Moiya McTier explores fictional worlds by building them with a panel of expert guests, interviewing professional world builders, and reviewing the merits of worlds that have already been built. You're going to learn and laugh and gain an appreciation for how special our planet really is. You can subscribe today by searching Exolore on your podcast app or by going right to exolorepod.com. Okay, back to the show.
The mirrors themselves, each of those segments, they're made of beryllium, and then they're coated in a really thin gold layer, 100 nanometers thick. And 100 nanometers is 1/1000th the thickness of a human hair.
That's very thin.
Very thin. They took like a tiny little piece of gold. It's the same mass as a golf ball, so...
Okay.
It's much smaller, like probably a chunk of gold smaller than a penny.
Yeah.
In like sphericalness. And it, that's a word.
Yep.
So they basically took that gold, melted it down, and then let the liquid like slosh over the top just to get that really thin coat.
Why did we need the gold?
There's a reason that a lot of instruments, scientific instruments, use gold. It's also used in a lot of like chips for things. Because of its high electrical conductivity. It's 71% as conductive as copper, and it's inert, so it doesn't interact with a lot of other elements.
All right. Perfect.
It observes in the wavelength range from 0.6 to 28.5 micrometers. Micrometers and microns, same thing. It just means 1/billionth of a meter. But that wavelength range is the near and mid-infrared part of the electromagnetic spectrum, and that's the part that's really good at seeing through dust and gas, so it can let us see really distant galaxies. It can also let us see through our own galaxy pretty well, and so we could look towards the center of the Milky Way. It has this sun shield that I mentioned before, and the sun shield is large enough to cover the whole thing and like hide it from space. It's basically like a big cloak, and it's about 70 by 45 feet. Because even out in space, the sun has enough energy that it would heat up this instrument more than we want for it to get really good measurements. Because when you have more heat, then the electrons get excited, and the electrons can actually add noise to the measurements that we take with the instruments.
Ooh.
That's why a big cost in these missions where you're trying to get really precise measurements, a big cost is cooling things down, because you're trying to get the instruments as cold as possible so that the electrons aren't as happy.
Yeah.
So we want sad electrons for our science.
I mean, my computer fans are always like on turbo mode, ready to take off, fly away.
Just fly away. Speaking of flying away, the JWST has flown away beyond the orbit of the moon. So it does not orbit the Earth, and it doesn't orbit the moon. JWST actually orbits the sun at a point in space called the second Lagrange point. Lagrange points are these really stable positions in gravity fields, so they get pushed and pulled just the right amount by different bodies, in this case the Earth and the sun, so they can stay in the same relative position without expending any fuel or like thrusters to keep itself there.
Oh, cool.
Yeah, so JWST orbits around that one point, so it's always on the other side of the Earth from the sun.
Okay.
And then its sun shield can always be like pointing in that one direction, protecting it from the sun. It took about 30 days to reach that point because it's 1.5 million kilometers away, which is almost 1 million miles. And once it reached L2, which is how astronomers like say that in shorthand, it had to do this amazing kind of anti-origami like unfolding, you know, or kind of like flower petals blooming, because it was all folded up when it was launched. And so after it launched and after the rocket pieces like broke away, the solar panel had to come down. It uses solar power to charge itself. And then the solar shield, which was in different pieces, had to unfurl and then like combine. And then the mirror segments had to like, it's almost like they were put down like the legs of a tripod, and they had to be brought back up and combined around the mirror. Like everything had to be put together while it was in space without human involvement. So it just had to be programmed beforehand.
It feels like a lot that can go wrong.
Yeah, that's why people were having nightmares about it. And that's why it took so long to launch.
I can't imagine being that nervous.
Yeah, I'm sure many ulcers were formed, unfortunately. It probably didn't help that they were also drinking a lot of coffee to keep up to date with the announcements and everything.
It's a tummy trouble central.
Yes. And I already have enough tummy issues. Like, I'm so glad I didn't work on JWST. I would have been a mess. There were people whose entire PhDs really hinged on this one thing working correctly. And if just one thing had gone wrong in that unfolding, it would have been a wash. Like the Hubble Space Telescope was able to be fixed because it's much closer to us. In order to send human beings out to L2 to fix something like that just would have been really difficult. So, nah. So we got one shot and it worked. And now we get to use all of the powerful instruments that were on board in this little capsule that held them all. And each of these instruments is like person-sized. Not large person-sized, but like they're big. And the enclosure they're in is at least as big as the mirror, right? So this whole thing is large. It's almost 14,000 pounds. But there are 4 instruments. There's the near-infrared camera and the near-infrared spectrograph. And then there's the mid-infrared instrument, which has both a camera and a spectrograph, and there's a sensor. So let's start with the near-infrared camera. This is meant to detect light from the very first stars and galaxies in the universe as they were forming, so that we can learn more about those processes early on. It can also help us learn about the population of stars in nearby galaxies, because it's going to peer through all of that gas and dust. And it'll let us study young, newly formed stars in the Milky Way, again, because we can peer through all that gas and dust. It's also going to let us study some objects in the Kuiper belt, which is that big belt of debris outside the orbit of Neptune, kind of like the asteroid belt, but further out. The camera also has a coronagraph, which is an instrument that can block bright sources of light so you can see the fainter stuff around it.
Cool.
Coronagraph like that was derived from specifically looking at our sun, so that you could block out the sun's corona when you were trying to look at other objects around it. But it's now more generalized to blocking all bright objects. So that's the near-infrared camera. Then we have the near-infrared spectrograph, which takes the spectra of all those same stuff that the camera sees, but it's designed to observe 100 objects at the same time.
Too many.
It honestly probably isn't enough because there are billions of galaxies that this telescope wants to study, maybe even trillions. And so seeing as many as possible at once just makes it more efficient. And the technology that they used to do that was innovative. It was developed for James Webb. The NIR spectrograph is the first to use something called a micro-shutter array, which lets the system strategically close tiny little, I'm going to call them eyelids. They're tiny little eyelids so that it can focus on distant objects. And the paper that I read, or the article that I read describing this, kind of compared it to squinting. They can use electricity to individually open and shut all of these 100 different arrays, and then they can shut specific ones to just focus on distant targets. Does that make sense?
Yeah, I'm imagining how sometimes I'll squint to focus.
Yeah. That comparison helped me.
Yeah.
So the mid-infrared instrument has both a camera that's really wide field, so it can see a bunch of the sky at once, and it has a spectrograph on it, and it's good for seeing the red-shifted light of distant objects, like galaxies. It can also see newly formed stars, and it can see really faint comets and objects out in the Kuiper belt. And this is the camera that's responsible for giving us the most stunning images from JWST. So thank you to the mid-infrared instrument, or MIRI, as some people call it. Thanks, MIRI. And then there's a combined instrument, and I'm not totally sure why these are together, but they're one instrument, and it's a fine guidance sensor, but also a near-infrared imager, and specifically slitless spectrograph.
I don't like
they
that
really
word.
Emphasized it. I don't.
Not the word for me.
So it's a spectrograph, but it doesn't have the slit shape to let the light in, kind of like the double slit experiment. Like it's not doing that. It's a spectrograph that works in a different way. Mm-hmm. But this sensor/spectrograph combo lets the telescope point really accurately at a given target, and the spectrograph's goal is to detect the first hints of light in the universe, but also to detect exoplanets. So JWST has directly imaged at least one exoplanet that I know of, and then it can characterize those planets and study the spectra of those planets' atmospheres, so it can do a lot. Such a powerful telescope altogether. And because it's really powerful, a lot of people want to apply for time on this telescope, and pretty much anyone can. I'm not sure if you need to be affiliated with a research institution. If you aren't, you might need to be vouched for, because they just want to make sure that the time is going to professionals. So they put out a call for proposals every year, and then they operate in cycles. They just started the 3rd cycle of observations after the 3rd round of proposal applications. researchers who aren't directly involved with the JWST, like who aren't actually part of the team, they can apply for time through the General Observers Program. They usually award about 6,000 hours to general observers, and the proposals there are due in January, and then that cycle would start observing in July. So they just started the third cycle of observations that will go through June of 2025, and then they will start observations for cycle 4 in July of 2025. For the first 3 cycles, so this is going to be done after next summer, but right now, 16% of all of the telescope's time is guaranteed to go to researchers who helped develop the software and the hardware for JWST, which I think is really fair. They spent so much time and effort just pouring it into this telescope, so they get to reap those benefits of having guaranteed time. And then, like many other observatories and telescopes we've talked about before, there is director's discretionary time, where the director gets to decide how to use the telescope in like short moments for really potentially more risky types of observations. Mm-hmm. The director of JWST from 2018 to 2022 was Greg Robinson. He's a black scientist who went to an HBCU. He lectured at Columbia, and I'm really glad that he was one of the directors for JWST for so long. But he stepped down in 2022, and now there's no program director for all of JWST, but the acting project manager is Kathy Barclay. So I'm wondering if they're in like a time of flux or if they need to appoint new people.
That feels like a long time to go without a director.
Yeah, I agree. Or maybe I'm just not as good at Googling as I should be. But I looked through their site. So those are like the specs and characteristics of JWST. I feel like I answered all of the questions you had. Did any other questions come up?
A question I didn't know I had was like how the time is allocated, because we've always been talking about that. So that was fun to learn. And congrats to those who recently in their last few weeks got their cycle going.
Yay! All of the projects that have been awarded time for JWST, they're publicly available. So you can go online. The link is available for patrons in the research notes, but you can go online and see who's been awarded time and what they're trying to observe.
Ooh, fun.
And in the past, some people have kind of gotten scooped because they've, their observations were publicly available. Not the data. The data is proprietary for a while, but just when other people know what you're looking at, it kind of gives them a hint.
They're like, I want to look at that.
Yeah. Or like, I want to go back to the archives and see what data exists on that object.
Yeah.
Mm-hmm. So, you can be pretty sneaky. And that is the part of science that I do not like. That is one of the reasons I left.
I don't like that either. I wouldn't want to publish like a script I'm working on or like a log line and then, I don't know.
Yeah.
That would make me feel very upset.
Okay. I'm glad that we covered pretty much what you wanted to know about JWST. There is some extra stuff that I want to tell you because I said that they changed the name in 2002 from the Next Generation Space Telescope to JWST. And I also said that I don't really like to use the telescope's real name. So let's talk about why.
Yeah.
In 2021, I think in March, several astronomers, including Drs. Chanda Prescott-Weinstein and Lucianne Wakowicz, they wrote an opinion piece, but it's behind a paywall, so I couldn't include it in the research notes. But they wrote this opinion piece saying what people had been complaining about for years up until that point, that JWST's name should be changed because the telescope was named after a not very nice person. They distributed a petition. It got almost 2,000 signatures from astronomers around the world, and yet the name was not changed. NASA refused several times up until 2022 to change the name of this telescope. So the reason that people had been complaining for years about this name is because the telescope was named after a man named James Webb, who was a former NASA chief administrator. He led the agency from 1961 to 1968. So during the Apollo era, he retired just a few weeks before Neil Armstrong and Buzz Aldrin walked on the moon. And he oversaw more than 75 other missions at NASA. So he was a celebrated NASA administrator. But before he was at NASA, Webb was the U.S. Undersecretary of State. And there's archival evidence that shows he was complicit in something called the Lavender Scare. Have you heard of this?
I have. This is mortifying, but this is how I've heard about it. The Swiftie community, there's a I don't even know, a conspiracy. Like, people are always trying to, like, unravel Taylor Swift Easter eggs. If they're Easter eggs at all, we might be grasping at straws.
You're part of this community, self-claimed.
There's one where, called Gaylor, where they think Taylor Swift dated Karlie Kloss for a while. And whether or not she did, some of the reasons they think she did was that she used lavender haze in a song. Like, her references to color can often align with, like, descriptions of the bisexual flag or the lesbian flag or the lavender scare or things like that. So whether or not I believe in Gaylor, I do think it would be so fun if Taylor Swift was bi.
Yeah.
The bi community needs Taylor.
I don't know if we do, but sure.
We're doing fine without her. But that's how I've heard about it.
That's hilarious. So, yeah, lavender is the color often associated with the, like, queer version of events. So I attended a lavender graduation, which is like the graduation ceremony for queer folks in college. And this lavender scare is like the queer version of the Red Scare from the 50s, when people were really scared about communism. And in America, like in the government, they were seeking out communists, persecuting them, and then removing them from their positions. And the lavender scare was something similar, where in the 50s and 60s, I think, maybe 40s, they were persecuting queer people in government positions and removing them from their jobs. And there is evidence that Webb was complicit in all of that. The astronomers who wrote that opinion piece, they suggested that the telescope's name should be changed to honor Harriet Tubman. And that got a lot of support, but NASA absolutely refused. Some of the justification was that there wasn't sufficient evidence to besmirch Webb's name, although that's like debated.
Yeah.
They also said that if they were going to name the telescope after a person, it should be an astronomer, and Harriet Tubman isn't an astronomer, to which people said the very valid pushback of James Webb wasn't an astronomer either. He was an administrator at NASA. He didn't do research. And honestly, Harriet Tubman used more astronomy in her work, to navigate and to tell time than James Webb did. So that point was silly. But yeah, this is a sore point for a lot of astronomers. There are many, like me, who, as much as possible, refuse to say the telescope's name. And this has, like, the debate goes back and forth.
Yeah. That's disappointing.
I know. And also, I would have really loved to use the Harriet Tubman Space Telescope.
Yeah, same.
Yeah. That would have been so nice. But unfortunately, we can't. The name is what it is, but despite that, the telescope has made some amazing discoveries, because it, at the end of the day, is a chunk of metal out in space. It doesn't care what it's called. It just wants to look at the universe. And so it's made some pretty cool discoveries, and I have here like 3 of the most exciting ones that I pulled out. One is in a big area of research that JWST was meant to cover. It's on galaxy formation and, like, what's going on with galaxies in the early universe. And one of the biggest findings from JWST that got a lot of media attention, because journalists love when they can be like, are astronomers wrong about how the universe works, was that galaxies may have formed faster than we initially thought. We talked a few weeks ago with the Dr. Beatrice Tinsley episode about how our understanding of galaxies has shifted over time. She was one of the first people to say that they were dynamic in nature, that they can evolve over time. And that led us to this model of gradual gas accumulation, where over many millions of years, a galaxy that's really just a collection of gas and stars will gather more stuff through its gravity. But JWST observed galaxies that were bigger and brighter than expected when the universe was less than 1 billion years old. And so we have to figure out what's going on there. Like, in the early universe, was star formation easier? So maybe they were able to build up faster. Was there something different about the medium of the universe that made it easier for stuff to accumulate? Like, I don't know. We do know that the driving mechanisms of the universe change over time. Like, now we're in a period of dark energy expansion. Before, we used to be in a period of radiation dominating the behavior of the universe. So we just want to know what was going on way back then. So that's galaxies, but similarly, supermassive black holes were seen earlier than we expected because those also need time to build up, or so we thought. But maybe the galaxy merger rate was much higher back then, or maybe there was something about what was around those black holes that made it easier for them to combine. Like, if there was less or more stuff, maybe dynamical friction would let them merge earlier. Like, it's an open area of research now that we know this is something to look at. And now that we have the tools to look so far back in the universe. A new type of object was discovered, potentially, called jumbos.
Love them immediately.
Right?
What are they?
This is an acronym. It stands for Jupiter Mass Binary Objects. JWST found about 40 of these jumbos in the Orion Nebula. These are objects that are planet-sized, so like Saturn and Jupiter-sized, but they have binary companions, so they're orbiting with other things about their same size. And that's really strange because our current models of star and planet formation don't predict this. We don't predict that stars that form at the same time should get that small, and we don't predict that planets, if they were to somehow be ejected from their star system, that they shouldn't keep their pairs together, that like the pairs should be ripped apart if they're getting flung out of their system.
Sure.
But we don't see stars around them. So what is going on? Like, it's just a very weird thing. And it's just 40 of them in this one nebula that we've been able to find. So I will be looking out for more jumbo news in the future.
Yeah, me too. That name is too cute to ignore.
It is. And then JWST has done a bunch of stuff with planets both in and out of our solar system. It took this really beautiful image of Uranus showing at the northern pole some dynamic features. So it was one of the things that showed us that there are these cool atmospheric dynamics happening. Before, we didn't really know that because Uranus just looks like just a plain blue surface. So it's hard to tell if anything is going on under there. But JWST also looked at exoplanets and their atmospheres, and it detected molecules like methane, carbon dioxide, and dimethyl sulfide in the atmosphere of a planet called K2-18b. This is a rocky planet that orbits in the habitable zone of its star, so it's the right distance for liquid water to potentially exist on the surface. But we don't know if there's actually water there unless we can see it or unless we can get some spectral evidence. And this was the spectral evidence that we needed to say, oh, there's a chance now that this planet could have a surface water ocean.
That sounds cool to me.
It is cool. It's exciting. As an exoplanet girly, I am always here for learning more about the surfaces of other worlds. So those were like the top discoveries that I pulled out, but I included a chronological list of the big papers and discoveries from JWST for our patrons. So check that out. And if you're not one of our patrons, then sign up and you'll have access to these cool resources. But that is all I had to say about JWST.
Well, it's a really exciting tool, and I can't wait to call it the Jelly Welly forever.
Yes. Oh, I love that. Awesome. Well, next week we are going to continue talking about the JWST, but with a special twist. So come back next week. I'm sure you will. But until then, they're doing last call, so I think we should order.
We better get one before they go.
Yeah, we're going to order another drink. So listeners, no matter what your cocktail or mocktail drink of choice is, remember, you're still space.
It's true. Bye.
Bye. Hail Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.